Today you're going to be learning about the terms period, frequency, oscillation, simple harmonic motion, equilibrium, and how pendulums work. You'll also be discussing what causes pendulums to change in their period. So today's lesson is called simple harmonic motion. When something is said to repeat itself, repeat over and over again, kind of like how the sun rises in the east in 24 hours, it's going to rise in the east again, and does that continuously, is said to be periodic. We can also think, and this is talking about how it repeats in a certain amount of time. Clocks, they tick, the minute hand goes around in 1 hour, the second hand goes around in 1 minute. That is also said to be periodic. The moon goes through all its phases and repeats itself in 1 full month. This is referred to as periodic motion. Now, the time it takes for this is called the period. So the period is the amount of time it takes to repeat, like first period. It's the 24 hours where you repeat first period. Now, period is symbolized by the letter T, not the letter P, which is confusing. The letter T is used because period is a unit of time. So it's the time it takes, and it's in seconds. And so the period is always time, t, and it's measured in seconds. So we always calculate what is the period of this object in seconds. So let's watch an example of periodic motion. So when an object oscillates or moves back and forth about an equilibrium, we call this a simple harmonic motion. Now, what an equilibrium is when the objects stop moving. If you were to suddenly just stop it, it would go to the same location every single time. For example, a pendulum. If you were to stop a pendulum, it would go straight down. It's not going to be left, it's not going to be right, it's right down the middle. On the other hand, if you take the rotation of the moon around the Earth, if it stops, it's not going to go to the same location. If all of a sudden you pull out a battery out of a clock, it's not going to suddenly all go to, all the hands go to one location. It's just going to stop. So certain things can have a repeating pattern and be periodic, but not be simple harmonic. So the two requirements for simple harmonic is, first, it has to have an equilibrium. If it stops, it will go to this location every single time. And secondly, it has to oscillate, move back and forth. It has to repeat itself. So in 1678, Robert Hooke put a spring on some mass on a spring, pulled it down, and he realized that it went up and down in a spring-like fashion. And that, again, has that simple harmonic motion. If you take that weight off and just let the spring hang, that's its nice natural position. But if we were to just, it's not compressing the spring up and it's not pulling it back down, those are kind of going ups and downs. That spring is in that state of equilibrium. And if you were to displace it and cause it to move up and down and wiggle, then it has that simple harmonic motion. So let's show a video of that. Alright, so pendulums, as we said, are simple harmonic motions, and our kind of anatomy of this, we got their string attached to a weight. That weight we refer to as a bob, short for Robert. And this bob, or plumb bob, is pulled out by an angle and let loose to go back and forth, back and forth. That then it's just going to go back and forth, and if there is no friction, it will continue to do so forever and ever. Now, in our lab we determined that the only thing that affects a pendulum's motion is the length, not the bob's weight. It's not how far of an angle we pull out, it's just the length. So we may have seen this type of a pendulum. It's in the Clark Planetarium, it's BYU, the U have them. Many universities have it in their physics building. It's called the Foucault pendulum, and it moves back and forth, And what's really interesting is the Foucault pendulum, named after Jean Foucault, did this demonstration where he determined that this pendulum, if it's a long enough pendulum, that the Earth itself will rotate underneath the pendulum, and the pendulum will actually rotate at slightly different things over the course of a day. So it will actually repeat itself over and over. All right, so now we're moving into some new vocab words. Cycle. What is a cycle? Well, a cycle is when you have that back and forth motion. It's that tick-tock of a swing. A period, again measured in seconds, it is time, symbolized by the letter T, is a measurement of the time it takes to do a full cycle. So it's how much time does it take to do the tick-tock. Frequency, symbolized by the letter F, is the measurement of the number of cycles in a given amount of time. Now, the relationship between period and frequency they are inverse related to each other, meaning that frequency is equal to 1 over the period, or 1 over t. Period then is also equal to 1 over t, or f. So period is 1 over f, or the frequency. They're 1/overs of each other, meaning they're inverse relationships. So if I give you the frequency, you can find the period by taking the 1 over frequency. If I give you the period, I take 1 over that t, that time, and that gives you frequency. Now frequency is named after, the units is named hertz, or symbolized by the letter Hz, named after this gentleman, his last name being Hertz. So let's practice some frequency problems. A young girl on a swing completes 20 cycles in 25 seconds. So we know that they have a number of cycles and a number of time. So our frequency is just the number of cycles divided by the time it takes. So if we take 20 divided by 25, that's going to give you 0.8. Then if you do, for the period, it's the time divided by the cycles. So you just take 25 divided by 20, which gives you 1.25. So it takes 1.25 seconds per every tick-tock on this swing. Another way you can solve it is if you take 20 divided by 25, which gives us our frequency of 0.8, and you do 1 divided by 0.8, that gives you, again, 1.25. It's just another way of solving it. All right, a clock clicks 88 times per second. So calculate the frequency and period. So I want you guys to do that. All right, so it is 88 divided by 22, which is, then of course, it's going to be 4. And that 4 seconds, that's going to be 4 times per second. So what's the period? Is then again 22 divided by 88, or 0.25. So that means it's a quarter of a second per click. All right, a strobe light, or what we call a stroboscope, has a time intervals of 1/80th of a second. That means it flashes on and off. It repeats on and off in 1/80th of a second. What is the frequency of that? Well, again, its time, or period, is 180. So we can put that in our calculator and we'll get 1/80th. So the period is 0.0125. The frequency is just 1 over that, and that gives us 80, which conveniently is exactly what we says here, 1 over 80. If you flip that fraction, it gives us the frequency of 80. Last one, a spring vibrates at 24,000 times in 1 minute. What is the frequency and period? Now, this one's a trick problem, so I want you to think about it, pause the video, and do this problem. All right, so 24 in 1 minute. A lot of you will say, oh, the frequency is just 24 divided by 1, which is 24,000. That would be wrong, because you need to have the time needs to be in seconds always. So we need to change that to seconds. So it's going to be 24,000, but it's not divided by 1 minute, it's divided by 60 seconds, which gives you 400. So its frequency is 400. Now, you take that 60 divided by 24,000, or the frequency of 400, and do 1 divided by that, and that gives you the answer of 0.0025. So its period is 0.0025. So, remember, frequency is cycles per second, not minute. All right. If you have any further questions, please ask your teacher. Thank you.